Hello and welcome to Physics Teacher. In this grade 11 functions math tutorial, I'm going to be going over vertical and horizontal translations, compressions, and stretches. So stay tuned. Alright, first off, let's look at the effect of this translation here on the function. We'll look at a couple examples. We'll try a quadratic, so we'll do basic x squared, and then we'll add some constant to it or subtract. We'll do a inverse function, such as 1 over x, and then same thing, we'll add some constant. And we'll also do a radical function, like so, where we will add some constant. Let's see what happens. All right, so here I have the graph x squared, and now if I were to take x squared and simply add 2, you can see the graph has been translated up 2 units. Well, what if I were to subtract 2? What would happen then? Here it gets translated down 2 units. Now let's try the same thing with the inverse function. So there's our inverse function, 1 over x. And for this one, if I do 1 over x plus 2, what happens? Same thing, it gets translated up 2 units. And lastly, we'll try our radical. So there's our radical function. And if I add 2, it gets translated up 2 units. So as we see, C is a vertical translation of the graph. If C is positive, the graph moves up C units, and if C is negative, the graph moves down C units. So now let's look at how the value of D changes our function in this scenario. We'll do the same scenario, but in this case, if f at x is going to be x squared, we are not going to simply add a term here. When we translate it, g of x is going to be x minus some value d squared. Similarly, if we apply this to our inverse function, 1 over x, and we translate this one, g of x, we're going to look at what happens when we have 1 over x minus d here. And finally, we'll also look at our radical function. And when we translate it with d, our new function will look like so. Let's take a look. All right, so there we have our x squared function. Now if we look at what x, let's do 2 again, add 2 and square. It looks like it moves it horizontally to the left for a positive value. Well, that's interesting. What would happen if I made it negative? So let's add another function, x minus 2 squared. That one translated it to the right 2 units. Will this do the same for our other functions? Let's find out. All right, so there's our inverse function, and now let's do 1 divided by, we'll do x plus 2. And we get, looks like it shifted it to the left 2 units. And when we do x minus 2, it shifts it to the right 2 units. Finally, let's check this with our radical function as well. We'll start with x plus 2. And indeed, shifted it to the left 2 units. And if we do minus 2, shifts it to the right 2 units. So in this scenario, it looks like d is a horizontal translation of the function. Now it can be a little confusing, as we notice that our function g of x, when we made x plus 2 squared, this actually translated to the left. Typically we like to think of positive value being to the right, but that's why we throw the negative into the equation here. So in this case, the value of d is -2, because if we substitute -2 in for d, the double negative gives us a positive. So when d is negative, it shifts to the left. And if d is positive, which would be in this scenario, d would be +2, we have a shift to the right. All right, now that we're good with that, let's try some examples with it. We are going to try and describe the transformation in each of these 3 example functions, and then include a little sketch and state the domain and range. So our first one is our quadratic function. Here is our vertical shift. So our vertical shift, this is up 1 unit. And here we have our horizontal shift. Now it's positive, meaning the value of d is actually going to be negative. So always just think of taking the opposite sign in that bracket there. And if that d value is going to be negative, then we are going to the left 5 units. So just doing a rough sketch here. Let's take the vertex of that quadratic, which is usually at 0, 0. We're going to move it up 1 and then left 5. So somewhere around here is where we'll place our quadratic. Now let's check that on the calculator. So there's our parent function x squared, and now we're going to try x plus 5 squared plus 1. All right, so that looks good. Next, let's look at our inverse function. So here is our vertical shift. So we are going down 7 units. And here is our horizontal shift. Again, you can imagine there's brackets here, so take the opposite sign in the brackets. And we are going to the left 3 units. Now with our quadratic, it was easy to take the vertex and move it around. But what are we going to do with our inverse function? Typically our inverse function looks like this. Just a rough sketch here. And it has these coordinates here, which is 1 and 1. And right here, which is -1 and 1. So what we can do is sort of move those points. And so let me redraw this below. You can almost also imagine kind of moving your coordinates over a bit too. So we're going to go down 7 units. We're over here. And to the left 3 units, roughly here. And so our new points will be here and here. So rough sketch like so. And now we can check that on our calculator. All right, so there's our inverse function, parent function 1 over x, and our new one is going to be 1 divided by x plus 3 minus 7. There it is. Looks good to me. Now our radical function, it looks like we are moving up 4 units. And this one would be to the right 2 units. Now typically our radical function, or just the square root of x, will look something like this. So we have the point 0, 0. And we also have the 0.11 as well. So let's translate those ones for our rough sketch. If I do that, 0, 0, we go up 4 and right 2, so somewhere around there. And 1, 1 is here, so it looks like something like this. And finally, let's check that on our calculator. All right, there's our radical function, and now we're going to try translating it with the square root of x minus 2 plus 4. All right, perfect. Now let's try some compressions and some stretches. All right, now let's take a look at some vertical stretching and compression. And that's going to happen with this a value right here. So we're going to take a look at what happens if a is greater than 1. In our three situations, we're going to use 2 in our quadratic, our radical, and our inverse. So let's take a look at this in our quadratic on our calculator, as we're already fairly familiar with them from grade 10. Now we can also take a look at some function, let's call it h of x, when that value of a is between 0 and 1, say 1/2 x squared. So what's going to happen here? Let's look at it on our calculator. All right, so let's start by graphing our parent function, x squared. And next to it, we will try 2x squared. Now on our calculator, initially they look the same, but if we look closely, you'll see that the y-axis is slightly different. So let's change the view. There, so now we can see the y-axis only goes up to 8 on both graphs, and we can clearly see now that our 2x squared graph is being stretched vertically, like that. Now let's see what would happen if I change the a coefficient in our second graph to 1/2 instead of a 2. You can see that our black graph here has been compressed vertically. Now let's do the same for our radical function, but let's look at this with a chart. So we're going to do g of x is 2 times the square root of x, and let's also look at h of x as being 1/2 times the root of x. So let's create our little chart here. All right, so in our chart, I'm using x values 1, 4, and 9. They're simple because I know I can easily take the square root of them for our parent function f of x. So this is just going to be 0, 1, 2, and 3. Then what happens when we have this 2 in front? Well, it's twice that amount. So we have 0, 2, 4, and 9. So we can clearly see that these values are being stretched vertically on our y-axis. And what happens when it's 1/2? Well, we've got 0, 1/2, 1, and 3/2. So here it's being compressed. So if a is going to be greater than 1, we have a vertical stretch. And if a is between 0 and 1, we have a vertical compression. Let's take a look at that and confirm it on our graphing calculator. Now let's check our radical function. So I'll put in the parent function. square root of x. And then I'm going to add another one, which will be twice the square root of x. And finally, we'll put in 1/2 the square root of x. So here you can see the 2 root x is being stretched vertically, and the 1/2 root x is being compressed vertically. Now let's do the same. We'll check our graphing calculator with our inverse function, and we'll do it for both a stretch and a compression. So you can see our blue, which is a value of 2, is being stretched vertically, and our red, which is half that value, is being compressed vertically. Next, what we're going to do is we're going to analyze horizontal stretching and compression, and we're going to do so with this coefficient k. Now we can have k equal to a number between 0 and 1, like right here, or we can have another function, h of x, which will equal, let's take a value larger than 1 as before, we'll do 2x squared. Now you can probably guess already by doing a little bit of algebra what this is going to look like, but let's take a look at it on our calculators. So our quadratic on our calculator, let's start with x squared. This time I'll put them all on the same graph. Now for our quadratic, our middle one is our parent function, and then our pink one looks like it's being vertically stretched, but I want to talk about horizontal stretching and compressing. So this one is actually being horizontally compressed, and our green one is being horizontally stretched. Now let's analyze our radical function, again just as before with a chart. Now I'm going to pick x values 1, 2, 4, and 8. So it'll work out easier for us. The square root of 1 is 1. I'm just going to leave this as root 2. This will be 2. And the square root of 8 will be, you can just write root 8 or 2 root 2 if you prefer. Now, when we first multiply x by 2 and then take the square root, we start with a value of root 2. And then we have 2. And then root 8. Which is 2 root 2, and then 4. It's an interesting pattern. And finally, over here, we have the square root of 1/2, 1, root 2, and 2. Again, an interesting pattern. Let's take a look at what this pattern shows us. Let's just look at the value of 2. So when the y value on our graph is 2, in our original parent function, that value exists when x is 4. But when we put a value of k greater than 1, we can see that it now exists when x is 2. We've pushed it inwards horizontally to the value of 2. So this is going to be a horizontal compression. And when we put a value of k that's between 0 and 1, we see that that 2 occurs all the way over when x is 8. So now we are stretching it horizontally. So this will be a horizontal stretch. Let's confirm this now on our calculator. So now we can see that that root of 2x is being horizontally compressed, whereas the root of 1/2 x is being horizontally stretched. And finally, let's see what our horizontal stretch and compression looks like for our inverse function on our calculator. So again, we can see that the 1/2x, that black one, is being compressed horizontally, whereas the 1 over 1/2 x is being stretched. Finally, let's do some examples where we're going to take what we've learned on transformations and translations and combine it all together to sketch this graph. So here we have a quadratic. The parent function is just x squared. And our transformed function g of x looks like this. That looks like a handful, but let's break it down. This 1/2 here is a vertical compression. This 4 is a horizontal compression. This 3, and remember it is +3, not -3, as we would write our overall formula to look like this. Y equals A times the function of k x minus d plus c. So because in our formula we have x minus d, the value of d is actually +3. So that is a horizontal shift to the right, 3 units. And finally, this -2 is a vertical shift down 2 units. Now, since Desmos is much better at drawing curves than I am, we are going to graph this on Desmos, but I'm going to show you how each transformation occurs one at a time so you can do this yourself. Now, it is important that you apply any transformations before any translations. And the reason for this is a transformation, meaning a stretch or a compression, is multiplying or dividing by a certain factor, whereas a translation is moving left or right, up or down. It's addition or subtraction. And just like with BEDMAS, you do multiplication, division before addition and subtraction. So here all I've done is graph the parent function x squared. But what we are going to do is we are going to follow a specific point. Let's follow this point here, which has the coordinates 2 and 4. Now, when I apply my first transformation, this is a vertical compression. So let's look at what happened to our point here then, which was originally 2 and 4. It gets compressed by a factor of 1/2 all the way down to here. So what we do is we take our y coordinate and we multiply by 1/2. And that gives us 2 and 2. Now let's apply our next transformation. Our next transformation is a horizontal compression. So this is what happens. Now, following our point here, 2 and 2, since it's a horizontal compression by a factor of 4, what we're going to do is take our x coordinate and we're going to divide by 4. So that now gives us the coordinate of 1/2 and 2. Now that our transformations are out of the way, let's do some translations. So our first translation is to move to the right 3 units. So from here we take our position, which was 1/2 and 2. We are going to add 3 units to our x coordinate. So now we have the point 3.5 and 2. And finally, we'll do our vertical translation, which is moving down 2 units. So our point here has moved down 2 units in our y coordinate. So we've subtracted 2 units from our y coordinate. Whereas now it's going to be 3/2 and 0. So you can do that for a few points on your graph so that you can properly graph it all, but that is how you will apply all your transformations and translations. Now finally, we are going to write the equation for this graph that we sketched because we cannot leave it in this form here. So when we do that, we're going to have g of x is equal to, so we have that 1/2 times this function. So we're replacing the x with 4 times x minus 3, and then we're going to square all of that. So 4 times x minus 3, and then we're going to square all of that. And then we have to subtract this 2 at the end here. So if you want that in standard form, now we just have to expand that a little bit. So we have 1/2. 4 squared is 16 times x minus 3 squared minus 2. 16 over 2 is just 8. And this is a perfect squared, so we have x squared minus 6x plus 9, subtract 2. So that gives us 8x squared minus 48x plus 72, and then we still have that minus 2. So finally we have 8x squared minus 48x plus 70. Well, I hope that video helped. Stay tuned for my next tutorial, which will be on reflections and inverses of a function.